Okay, so for right now we will use Fg equals mg to find the gravitational force on an object, and little g will be 9.81 meters per second squared as long as we're at or near the surface of the Earth. This big equation, gmm over r squared, though, explains why little g changes when you go to the International Space Station, or if you go to Mars, or you go anywhere else, right? If you remember from grade 11 physics, little g changed at the International Space Station. It was smaller. Well, of course it was, because the r was bigger, and that would make little g smaller. If you go to Mars or the Moon or somewhere else, then both the mass of the object causing the gravity, like instead of the Earth, it would now be the mass of the Moon or the mass of Mars, and it's the radius of that object changes, and so then little g also changes. Okay, so we'll come back to this when we get to planets, but I showed you all that so you would understand why we use this Fg equals mg. It's just a simplified version for as long as we're at or near the surface of the Earth, or whenever we know the little g at some other spot. Remember from grade 11, this is the gravitational force of attraction, or the force of gravity. It is also known as the object's weight. Okay, so whenever it says the word weight, it's this guy. The two other forces that we talked about in grade 11 that will show up all the time, one is the normal force. Okay, Fn. Some people like to say the normal force is just equal to an opposite gravity. That is not the definition of the normal force. It is true that if there is an object sitting on a surface, like your book on the table, and no other forces are acting on it, then the normal force will be equal in opposite gravity. But what the normal force really is a force of the surface pushing back on an object to counterbalance the force that that object is putting on the surface. And it is always, always, always perpendicular to the surfaces in contact. The word normal in math and in physics means perpendicular. So although this could be the normal force where it's equal and opposite to gravity, I could be pushing a book into the wall. This is the force I'm pushing with. This is gravity acting down. The normal force is the wall pushing back. So it does not have to be equal and opposite to gravity. Remember from grade 11 and soon in grade 12, if you were pulling a force at an angle, Fg was acting down and the normal force was acting up. So it's opposite gravity, but it's no longer equal because this force you're pulling with has a component in the x direction that's taking some of the weight off the surface. And so it would be Fn plus F, too bad I can't get my x and y's in the right direction, be Fn plus Fy that would end up equaling Fg. Okay, so don't say Fn is always equal to mg. Not true. It depends on the circumstances. Okay, so that's the normal force. Then the other force is our good friend, good buddy, friction. And remember, it's like the surface's protest to an object trying to move over it. So that if I'm pushing an object this way, then friction always, always, always opposes motion or the desired direction of motion, right? So if I'm trying to move an object, friction will work against me. If I am moving an object, friction will oppose that motion. Also remember there were three types of friction. One was static friction. One was kinetic friction. And the third was fluid friction. And the two we do all the calculations with are static and kinetic. Static friction is friction between two objects at rest with respect to each other. At rest with respect to each other. And what I mean by that is, it might be a box of your grandmother's fine china that you put in the back of your friend's half-ton truck. and you say to them, make sure it doesn't move while you drive it across the river to your grandmother's new home. And your friend's like, what do you mean it doesn't move? I'm moving it across the river. It has to move. But what you mean is, with respect to each other, you don't want this box sliding around on the back of the truck. What keeps it then at rest with respect to the back of the truck would be static friction. Okay, at rest with respect to each other. Remember that static friction has a limit. It varies up to a maximum limit. And once you hit the max, the object will begin to move, and then you have kinetic friction. So kinetic friction is when the object is moving with respect to the surface. Okay? If you remember from grade 11, static is always larger than kinetic. It's always harder to start an object moving than to keep it moving. It's easier to keep it moving. Both of these obey the equation FFR is equal to mu Fn, which is our fun equation, because in university they'll use FFR as the script F, and they'll use the normal force they usually just call a capital N, and so you get fun. Okay, this guy is the coefficient of friction. It ranges in values usually from 0 to 1. It tells you about how rough or how smooth the surface is. The closer it is to 0, the smoother the surface. The closer it is to 1, the rougher the surface. But the only time you see 1 or a little bit bigger than 1 would be like tires on concrete, on dry pavement. Okay, and if you remember from grade 11 in your book, there's actually a chart of the different coefficients. Okay, the same equation works for static and kinetic, it's just the mu's would be different. The mu for static for a given surface would always be bigger than the mu for kinetic, and that's why static friction is always bigger than kinetic friction. The third type is fluid friction. From chemistry, you should know that fluid is liquids or gases, okay, or I guess. And so this is friction that's an object that's moving through liquids like water or gases like air. Okay, so when we talk about fluid friction doesn't obey FFR equals mu Fn, because for static and kinetic, the surface area and the speeds do not matter. The friction will be the same. But for fluid friction, both of those matter. And what I mean by that is, imagine driving down Main Street. You're in the passenger seat. Put your hand out the window, and if you hold your hand flat facing the air, like with the palm facing the air, you'll feel a lot of friction. But if you hold it straight out, so just the side of it is facing the air, you'll feel very little friction. It's because surface area matters here. Okay? Then imagine that you're now still in the car, still in the passenger seat, but now you're driving on the Trans-Canada to Moncton. Put down your window and hold your hand out. The amount of air resistance you feel then will be much, much bigger because speed matters in fluid friction. The other thing that matters is the shape of the object. It's why cars and trucks tend to be streamlined. When minivans first came out, they were like straight in the front and they were like gas guzzlers. So now they're more streamlined so the air can flow up over them more instead of just hitting it. Okay, so because these three things matter, fluid friction does not obey this equation. There is actually not a one-size-fits-all equation for fluid friction. The equation changes depending upon the object and the situation. So it's why you will not calculate with an equation fluid friction in high school. You actually need calculus, so you'll have to wait for university to get that. Okay, tomorrow we will do a few equations with these to dust off the cobwebs. For today, I would like you to do that half sheet that I gave you yesterday, questions 1 to 3 for homework for tomorrow. Okay, and enjoy your snow day. Try not to hurt your arms too much shoveling today.